So you can hear it's working. It's making dots and dashes. And the speeds of the dots and dashes is working. Slower, quicker. And the gap, the delay system between characters, if I increase the gap to a second or something, you get a gap. Another gap. So it is working in terms of producing audio, producing dots and dashes, and so on. But it's producing garbage in the sense that they're too long, and it seems like everything is ending with 3 dashes and so on. So I think in the schematic, in the great scheme of things, the audio output and the dots and dash controls and the variable speed controller is working. The clock is working. The pattern, it's taking a pattern from memory here and then pushing it into bit by bit into a shift counter, and then sending that out to the audio chain. That seems to be working. What exactly the data being pushed is a question. This controls the length of the character, and since it seems to be pushing out 7 or 8 symbols, dots or dashes, that's a suspect component, because it should be 1 to 5 length at most, numbers and letters. The switch down here, this switch is definitely loosey-goosey. In fact, it's come off the board in 2 places, so that's not influencing the patterns. That's got to be repaired. And I have to investigate basically down here. I think this is the suspect part. The memory seems to be okay. It's pushing stuff out, maybe not all the memory, but then what accesses individual addresses is this chip. This counts through numbers 1 to 26, and then randomly pushes, or this PROM is switched on, sees the input counter, whatever number it is, 12, let's say, and then produces output memory from memory 12. So maybe this isn't working totally smoothly. So yeah, things to think about. All right, debugging blog, whatever this is. There's clearly a problem with this up-down 4-bit counter, because the second pin here on the output, if this is the 1s unit, the 2s, the 4s, and the 8s, the 2 is always high. This means that when you actually analyze the chip, the numbers that the counter is producing are 10, 11, which is 9 plus 2, because you've got this extra high 2-bit. You've got the 1-bit, 2-bit, 4 bits, and 8-bit lines. So the numbers you only get out, 10, 11, 7, 6, 3, and 2. So these are the address locations to look for Morse code sounds. So you're only looking at 6 addresses into the memory. There is an extra pin, the 16th pin here, that gives you the full access to all memory addresses. And that's controlled by this chip here. But this pin always seems to go low, which I think is wrong. And so you never get to the higher registry. So I got an example here where I'm going to force this pin to go high, and you'll be able to hear the different letters in the other addresses, the 16 plus 10 plus 11 plus 7 plus, so you get a whole bunch of other addresses, and hopefully get that caught on camera. So I'm going to simply force, I'll switch it on, and we're running, and I'm going to force 5 volts into that 16 pin, which is pin 14 on the memory chip, which is in here. And if I can do this, you'll see that maybe it's a bit too quick. Don't know if I can do this with one hand. Hang on. Yeah. You're seeing, you probably couldn't tell from the sounds, but those were different dots and dash patterns because they're coming from different address locations. Now, it's 16. Remember the previous pattern. If I go back, where was it? Let's find that pattern. Well, basically it was 10 plus 16 would be 26. 11 plus 16 is 27. 10 plus 16 is 26. Then you had 7 plus 16, which is 23. 6 plus 16 is 22, and so on. So just bumping all these numbers up by 16, you get access to different addresses in the memory and the different dot dash patterns. So the memory seems to work. It's just getting into it, which is not working. So I think the memory is fine, which is the big scary bit, because that's the PROM, which I'd have to find a programmer to deal with. And it seems to be the problem is in the counting the address locations chips down here, which are definitely pennies each. They still make them very easy to replace. All right, so one of the videos I posted describes the issue with this counter. Just to recap, here is the memory chip. It's a 32-byte, 8-bit memory. And this is the input address lines to locate an address. Then the contents of that address, those 8 bits, are then sent out. 5 bits are sent to form the Morse code characters, and the lower 3 bits, this is the upper 5, the lower 3 bits, least significant bits, are used to read the length of the character. So every address here has a shape of a character and the length, the number of dits and das to be performed with the audio circuit over here and so on. So when the PROM is asked to kind of wake up, look at the input address, find an address, and send the contents out, that input address decision has to be random. That's how you get the variety in letters and numbers. Now that is arranged because the chip and the associated circuitry about basically making interword spaces and dits and das and sending it to the speaker, that's all controlled by a regular master clock up here. But to get the variation randomness, they create a second clock down here, square wave clock, which is noisy. It's got a bit of jitter. It is making square waves. It is pulsing, but not in sync with this one. So if you're living your life off this master clock, this one looks a bit random and varied. And that's exactly what you want, because using that clock, it runs a counter chip. And that counter chip basically counts from 10 down to 1, and then it counts to 0, resets itself, and gets back to 10 again. So it's going 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 0 is sort of an unseen count, and back again to 10. So the input address basically goes from 10 to 1, 10 to 1, 10 to 1. Or you add a pulse of 16 on the 5th bit here. So you got the 1s, 2s, 4s, 8s, and 16s. This pulse of 16 gets you into 16 plus 10, so the 26, 25, 24, 23 registers, and so on. Now, that's the basic. This chip, however, the counter, this pin, pin 11, which is the 2's unit in the address counter, is always on. So it's never counting down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's counting 10, 11, 10, 7, 6, 7, 6, 3, 2, 3. And if you look at why that sequence makes sense, it's because if you write it out in binary and you always keep that B pin QB open or high, then you end up with a binary number which is out of sequence. It looks like 9 plus the 2 is always on makes 11. 8, it looks like 10 because you've got 8 plus the 2 is always on, it's 11. So it turns out if you flip open the board, down there you'll see right in the middle of that shot, I'll try and point to it. Give me a second here. Gotta hold it all together. Right down here, right where my thumb is, you'll see 2 pins that are tied together. There's actually a solder bridge right between them. I don't know if you can see that in the camera. That is causing a short. And when you count the pins, pin 11 and 12. And of course, if pin 11 is tied to pin 12, that is pull high. So now I understand why this counter is out of whack. What's interesting is it looks like that short. I mean, I can't imagine it's from the factory, but it's a really clean piece of soldering, suggesting it hasn't really been tampered with, although there was one or two pins that are a bit scruffy. Pin, what is that, pin 16, pin 14. But otherwise, yeah, really nice. So I'm going to clean that bridge, reinstall the switch that I'm currently dealing with down here. I'm just rewiring that in, cleaned it up a little bit. I'm going to take off some of this old solder, this old flux, and put the switch back in, and then we'll power it up. So this counter should do its job counting from 10 down. The next problem is to really understand what's going on in this flip-flop gate. These are two D-type flip-flops that run on chip 9, which is this one here. And right now, that chip is not producing correct values. So that's another investigation for another part of this, I don't know, video blog or whatever you want to call it. Bye. All right, so after the, turn the volume down. After identifying a short between pins 11 and 12 on the counter, if you remember the binary 2 pin 11 was always pulled high, and so this wasn't counting 10.9.7, 10.9.876, whatever, all the way down, because it was tied to pin 12, which is positive. So I separated the pins on the back of the board and hook it up for free running. And if I'm just going to probe the board. I'm doing the logic probing here. I'm going to sample. That yellow line is where the reload and the refresh happens. Let's go and find it. Bang. You can see now, I'll maybe find a better one. Find a better example, just to cross the I's and dot the T's. There we go, right at the edge of the board. You can just see it over there. That's where the board is flashed to reload, and it starts to count down. And you've got 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then you have the refresh. And if you drill into that refresh, let's find it. It's a tiny, tiny pulse. And that pulse is approximately 1 unit there, 500 nanoseconds on the scope, where you get a 0 pulse, and then the counter starts again from 10. So the counter is working. Excellent. Now the problem remains, it's not producing the right length. 1, 2, 3, 4. Yeah, not sure why it's getting the extra dashes on the end. Basically, everything on this board, sorry, I'm zooming in there. It's producing extra 3 dashes at the end. So the length, if I understand the way this thing is programmed, the PROM in there is programmed. It should be following the last 3 significant bits of every address memory should contain the length of the character, and it's not working. Let's figure that out. Okay, so where are we? It's making characters, but they're too long, kind of a weird shape. Let's go and try and create some letters out of this. Oops. Let me get some letters. Here we go. L. J. Y. D. What I'm doing is I'm shorting one of the pins to well, I'm not shorting it. Well, I am shorting it, taking it to high to see what we get. C, E, I, E, K, C, D, C, D, C, P, C, K, C, C, P, K, L, L, C, L, K, P, L, I, L. Okay, so if you listen, obviously you're getting long Morse codes that are not letters or numbers. But certainly the dots and dashes make sense. And if we just ground one of the pins to the positives, I'm taking the Q1 output, pin 1 output of this flip-flop, which I think is broken, and I charge it up. Those are letters. And interestingly, they're all coming from the higher registers of the memory, the 20s. And I was going quite quickly, but the sounds that you're hearing are all the letters that occupy dashes and dots in the beginning and essentially can fit within the shape of numbers. All the numbers in Morse code are in the higher registers of the memory. They're in addresses, I think, 26 to 17, which is what we're playing here. And it goes back to the bad behavior. So ultimately, I think what I've shown in the probing and examination, the fact that it's making, turn the noise down a bit, the fact that this Morse code trainer is making tone, is making sounds, is making the correct dots and dashes, that's from the audio chain here. This is basically the shaping of the sound and the output here. Obviously, it's getting power, so the power regulator and the power chain is here. There is activity between the chips, so the master clock up here seems to be working. And really, the fact that it can read off elements in the memory, that is this memory chip here, when an address is accessed, the 5 upper bits of that address contain the shape, the dots and the dashes. And they are sent to the shift register, and each one is then played one at a time, a dot or a dash. Whatever the first bit is, the most significant bit in this case, is executed in the audio chain, and then the bits behind it move over one. And then that bit, that now new leading bit, is executed in the audio chain, and the remaining bits are shifted over one. That's what that chip is doing. And clearly it's forming and executing well. This chip counts the 3 least significant bits in the memory address, so the B0, 1, and 2, so the 1s, 2s, and 4s column in binary. And it's the information in this section of the address that tells you how many dots and dashes to play from the given 5 elements that you could play. Now, for numbers, you want to play them all, because all the numbers have 5 bits of information. For letters, you only want to play 1, 2, 3, or maybe 4 bits from anything that's sitting in the memory. And that length is encoded along with the shape of the bits it tells you how much to do here. And this chip, which is another counter, basically lets this chip execute only for that set number of times. So if you wanted to read an address of bits, dots, and dashes, but you only wanted to do the first two because you're doing the letter N, da, dit, this counter will only allow you to count twice. You get the da out, you'll get the dit out, and then this counter will stop, prevent any more reading, and then ask through this circuitry for another address to be pulled out. So basically, all of this schematic is working. When we get down to the the variation and the control of the letters and the numbers. For a start, there's another clock down here. This clock is not regular. It's not the same as the master clock of the whole circuit. And so if you're living your life according to the regularity of the master clock, this thing seems to be pulsing away in different, out of sync and in a sort of unpredictable manner. And it's really this phase shift, if you like, and this continual phase shift, which gets the variation of letters and numbers out of this device. Ultimately, this is IC8, which is a counter. And you notice on the inputs, it's hardwired with an 8 gone with a 4 bits of input, 1s, 2s, 4s, and 8s. The 8-bit is a high. The 2-bit is tied to a high. So you have 10 on the input. In fact, this diagram, the circuit diagram, is not accurate compared to what is actually built into these devices. Pins 4 and 13 are actually unconnected to anything. They do not follow back to this area over here. But essentially, with 10 hardwired on the input, this counter, which is designed to count in binary and count down, it counts from 10 down to 1 and then would reload. And it could count back from 10 down to 1 and reload. And it does that reloading, and it looks at the input to reload. These are called the jam inputs. Every time the load pin gets a little pulse. And this circuitry here controls that pulse. So if it counts down from a number, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, it gets a pulse. Excuse me, getting over a cold. It gets that input pulse, is told to read the input, which is 10, and goes back to 10 and starts counting down again. Now, that should not always happen. It should happen when you need to count numbers. There's only 10 numbers, so you only want a variety of 10 numbers. But with letters, you need to get to 26 addresses. And that coordination of getting across the 26 addresses in the memory comes down to this flip-flop chip, IC9. There are 2 flip-flops in this particular chip. They both run independently. Essentially, when you select letters or numbers, these 2 chips, or 2 flip-flop gates, coordinate with the counter to direct the memory either to go up to the 20s by pulling this pin high, so you're at 20, or at least 16, plus 10 gets you to 26, and then it cycles through 10 addresses, 26, 25, 24, 23, down to 17, and then reloads back to 26. It reloads the extra 10 from this process of looking at the inputs. When you want to do letters, you need to go through all 26 addresses. And that requires you to look at the 26th address. So you go up, pin 16 goes high. Sorry, pin 14, which is the 16th units in binary. That goes high. This goes to 10. You count down 26 to 17. Then this goes to 0. This pin stays high. You get address 16. And then this pin goes off. And this pin, this chip, does not look at its input, does not get the load impulse, and therefore goes to its default mode, which is binary, and counts 15 all the way down to 0. Oh, sorry, to 1. At 0, it does a reset. So it counts 10 when you want to go from 26 to 17. Then it just counts 0 when you're looking at 16. And then this defaults to a binary count of 15 down to 1, and you get all 26 addresses. And that sounds quite complicated in terms of coordination. It's a bit like drumming with your left foot and your right foot. And that's coming from these two elements of the same chip. And it's this part of the circuit which is not working correctly. So it's IC9. So that's my debugging. We'll talk a little bit about some of the tools I used, and you know, maybe a little bit more time on the schematic. But I guess for this video, repairing this Datong D70 Morse Code trainer is coming together. Okay, so today's surgery is to replace IC9, which is this one here, from this board. I don't know if we can get underneath and have a look. There's IC9, not to be confused with IC10. Yeah. And I'm going to try and take out one of these pins and show you the process, and then maybe I'll show you the end of the process afterwards. What I'm using, the soldering gun. That is working. And I'm going to try and show. I'm going to do this here. Okay. No, down here. Let's have a look. And you can see one clean pin. So I'm going to do all the rest and then pop this chip out. And then we'll see about putting in a socket to replace that chip. And then putting in a new IC. Okay, solder's removed. Whoops, almost knocked the stand over. If I can get my fingers underneath it. Wiggle, wiggle. And there we have it. Some writing underneath. But this looks to be a plastic dip. Cool. Let's get the socket back in and replace this. Just giving it a clean up. And let's have a look here. Okay, now we're just using I was using some isopropyl alcohol here, just kind of cleaning up some old residual. You can see the kind of the orange brown muck. So just double checking, these three contacts here exist only on the top of the board. This contact does have a top and bottom, so through-hole connection to the pin. It's a little bit discolored, this bit of solder. So what I'm going to do is I'm going to resolder the pads, fresh little bit of solder on top, because when we drop the socket in, it's going to make mechanical contact push down against these contacts with that. You can just see that shouldered pin that sits there. You could, if you wanted to, solder them underneath. There's a bit of space there to get, you can see underneath. You can access the pins and solder the top layer as well. We'll see if that's necessary once it's in place, and if we need to add a couple of blobs of solder under there. So let's solder that in. Okay, that socket is in, and it's not too much higher. I've tested the continuity with these 4 top traces, and they're fine. So these pins connect with those traces, and underneath I've obviously tested. You can see my soldering work there.
I've tested the continuity of all the various pins, and they look good, and there's no shorts, it would seem. So should be able to pop in the replacement chip. But before I do that, I need to refit this switch. And I originally corrected the mistake. There was a problem there. Oh, there's the IC8 tag I was missing, looking for that earlier. I popped in some thicker wires here, a bit too thick. They don't have a little bit of give that the board needs to manage, so I'm going to replace those with a thinner wire. And once that is in place, that should be able to select numbers, letters, or a mixture, which should ask this chip to coordinate between the counter IC8 here and the PROM and so on. So fingers crossed. Let's see. Okay, so the switch is reinstalled. You can see it's soldered in. And the new IC9 is in. That dual flip-flop 4013. We're going to switch it on in the letters mode for the first time to see if it works. Huh. Unbelievable. It looks like it's working. Let's try the numbers. Yep, 4. 1. Coming a bit too quick, so let's slow it down a bit. 6. 8. 2. 4. It works! Oh, fantastic. So, really pleased about this. Having troubleshooted it, embraced the problem, identified the problem, this dead flip-flop, and there's the old chip and a dead chip. Yeah, curl its feet up. Very, very interesting. Might try to decap that, see if we can take a look inside, see if we can see the actual circuit. I'll have to see if we can do that with some acid. But yeah, it's working. So let's play both. A, 0, U, H, 5, 2, 6. It's going a bit quick, but hey, it's a tutor. I don't have to get the right answers. That's what it's for. Fantastic. Really pleased with the project. It's done. I can move on to other stuff. Take care.